Welcome back to our STL journey. This is day 12 and today's focus is on one of the most powerful data structures for solving problems where priority matters, the priority queue. Whether you are dealing with scheduling systems, graph algorithms, or anytime elements need to be processed by importance rather than arrival time, the priority queue is your tool of choice. We will understand how it works, how to use it for both max and min heaps, and how to tailor it with custom comparators for advanced use cases. A priority queue is just like a regular queue, with one key difference. Instead of serving elements in the order they arrive, it always serves the element with the highest priority first. That means the element with the largest value or smallest, depending on how you define priority, comes out first. Think of it like an emergency room. Patients are treated by arrival time, but by how critical their condition is. Behind the scenes, STL implements this using a binary heap, which is a complete binary tree structure optimized for such optimizations. In C++, the priority queue is provided as a container adapter inside the queue header. This means it wraps around another container, typically a vector, and modify its behavior to prioritize certain elements. By default, it works as a max heap, so the largest element is always accessible at the top. This is done using the less t comparator, which gives precedence to higher values. All you need to do is declare a priority queue in and start pushing elements into it. The heap property is maintained automatically. Let's look at a basic example. We declare a priority queue int to push three values 10, 20, and 5. The queue automatically arranges them so that the largest element, in this case 20, is at the top. When we call top, we get 20. After popping it, 10 becomes the new top. The priority queue ensures that each time you pop an element, the next largest one is promoted to the top. This is the default max heap behavior, simple yet powerful. Now, what if we want the smallest element to come out first? This is where min heaps come into play. By default, priority queue does not support min heap behavior, but we can achieve it easily using a comparator. We define the queue with three template parameters: the type of the elements, underlying container, and the comparator. By passing greater int as the comparator, we flip the default behavior. Now the smallest element always rises on the top. This is particularly useful in algorithms like Dijkstra's shortest path, where we want to always process the nearest node next. Let's quickly go over the performance. Accessing the top element, the highest or lowest priority, is a constant time operation. That's because the top of the heap is always at the root. Pushing a new element or popping the top element both take log n time, where n is the number of elements in the queue. That this logarithmic time comes from the need to maintain the heap structure through upheaping or downheaping. These efficient operations make priority queue a highly effective tool for real-time and large-scale computations. Sometimes you will work with more complex data, like structs or pairs, where the default comparison isn't enough. That's where custom comparators shine. A comparator is simply a callable object, typically a struct with an overloaded operator. This function takes two elements and returns true or false based on your custom priority rules. You might want to prioritize by deadlines, scores, weights, anything. By injecting your logic into a comparator, you gain full control over how elements are ordered in the queue. Here's a real world scenario. Let's say we are working with a list of tasks, each represented as a pair of integers, task ID and priority. We want our priority queues to order tasks based on their second value, the priority. Using a custom comparator, we define the ordering logic and STL takes care of the rest. Now when you insert task into the queue, they will automatically be sorted based on how urgent they are. This is a foundational skill for coding interviews and advanced problem solving. Before we move on, let's talk about some common mistakes. First, forgetting to use greater for a main heap. This will silently give you the wrong behavior. Second, calling pop before top. Remember, pop removes the top element, but it does not return it. So if you forget to call top first, you lose that data. Third, confusing priority queue with queue or stack. A queue works in FIFO order, a stack in LIFO, but a priority queue is based entirely on value-based ordering. Always keep that difference in mind. To solidify your understanding, try applying priority queue in practical problems. Start with the classic, find the top k largest or smallest elements in an array, a great way to get comfortable with heap usage. Then move on to something more dynamic, like finding the median in a stream of numbers, which requires two heaps. Finally, attempt merging k-sorted arrays, a common use case where a mean heap shines. These problems will not only build your STL skills but also prepare you for real coding interviews. The priority queue isn't just a classroom concept, it's used everywhere. In operating systems, it manages process scheduling so that high priority tasks run first. In network routing, it ensures critical data packets are transmitted with priority. In graph algorithms like Dijkstra's or Prim's, it ensures the most optimal node is always processed next. Even in AI simulations or event-driven systems, it handles the sequence of events based on time or urgency. Mastering these tools equip you to build systems that are fast, responsive, and smart. To wrap up today's session, here's your homework. First, solve two lead code problems that require priority queue. This will give you a chance to practice both max and min heaps in real problems. Next, simulate an emergency room queue where patients are treated based on severity. Use custom comparators here. And for those of you seeking an extra challenge, design a toggle-level priority queue, one that can switch between min heap and max heap modes at runtime. These exercises will push your understanding and make sure you truly own this concept.